Good morning, ladies and gentlemen. My name's Howard Parkinson, and I'm here to present a paper entitled "The Potential for Using Big Data Analytics to Predict Safety Risks by Analysing Rail Accidents," which is quite a mouthful. I'm here with my co-presenter, Dr. Gary Bamford. I've got 12 minutes, so I better crack on. We'll take questions at the end. Thank you. Right, what is the focus of the paper? We want to look at big data, and we want to understand why it's useful, and we want to cut through some of the hype that's been written about it. We then go on to establish a data taxonomy for the railway. We've looked at the railway, and we've looked at what data is available, and we've tried to categorise it so that it's useful. We've then gone on to look at accident models, and we've looked at the causes of accidents, hazards, and the actual accident, and how the cause propagates to the hazard and then on to the accident. We've then looked at 3 accidents which we've analysed, and we've looked at what the causes are of these accidents, and we've linked them to the data from the data taxonomy, which provided us with a lot of insight. Then what we've done is we've looked at each of the accidents, and we've tried to get a feel for what the big data-ness is of the accident. Is it big data? Is it not big data? Is it business as usual? Then finally we present our product that we are developing called the elbow tie model, and we explain how that works, and then we conclude. So, is there a new dawn in the way we look at railway safety? We have big data, and we have the notion of the Internet of Things. And for those who are not familiar, the Internet of Things is this notion of having intelligent assets with embedded sensors and interconnectivity between all the assets so that you can monitor them. As you can imagine, this generates a huge amount of data. And already we're talking about zettabytes, which is 1 byte to the power 27. These are massive numbers, and it's real. I read on the IBM website yesterday that in the last 2 years, 95% of all data ever generated has come into being. So you're looking at a massive exponential growth in data, and it's happening now. Didn't want to do that. You may be skeptical about this, and that's understandable. Things do get overhyped. Gartner has got this notional curve where you have the peak of inflated expectation followed by a trough of disillusionment. And with big data and the Internet of Things, I like to think that we're on this slope now, this slope of enlightenment, and we will reach a plateau of productivity. But I don't think there's any going back. Big data. Big data has been categorized according to 5 V's. Some people have used 3 V's, we've used 5 V's. And these categorizers are the volume, that's how much data is there, the variety, how many disparate sources are there, the veracity, what is the quality of it, how truthful is it, what is the value of the data, does it actually provide any insight, or is it extraneous? And also the velocity, how quickly does it come slowly, is it real time, is it historical? Right. So our data taxonomy, we looked at the railway, and we've come up with, this is probably non-exhaustive and it could be added to, but this is the type of data that is available. So we've got business as usual type data, we've got real-time condition monitoring, traffic flows, incident data, we've got maintenance data, we've got inspection data, we've got business data, finance, HR, we've got operational data, manning levels, service data, operational risk assessments, we've got social media, we've got Twitter, we've got LinkedIn, we've got Facebook, we've got external data, we've got supplier data, we've got maps, we've got works locations, we've got environmental trends, we've got weather, We've got location data, we've got health data, we've got training and education data. So we've got massive amounts of data. And some of these will be implicated in accidents. Some of them may not be. Some of them we don't know. But that's what we want to do. We want to get this big picture. Moving on to accident causation. This was from a paper by Michael Neal in 2007. He was president of the IMechE, I think, or maybe not. Anyway, he looked at 47 different accidents from various industries. Some of them, some of the accidents were in the railway, and he identified these 14 causes, which I quite like. And if you look at any accident, 2, 3, 4, 5 of these will be relevant. We looked at Ladbroke Grove. 5 of these were at play. And you can see how they map onto the data taxonomy. So we looked at Santiago de Compostela. I'll show you this. So I'm not showing you this gratuitously. I'm just showing you this because it makes us realise why what we're doing is valuable and why we need to take it seriously. What happened there? Well, I'm not going to go into too much detail about the accidents in this paper, in this presentation, but there was no real speed control, only the driver distraction, train stability issues, passenger survivability issues. And in our paper, we've linked data to these. We've looked at Hatfield, UK 2000, gauge corner cracking, not understood, lack of proper control in management and contractor management, poor inspection regime, and not acting on accident reports. Network Rail had forgotten, Railtrack had forgotten that they were I'll present this one from Pleasure de Castelldefels in Spain in a bit more detail. So this was in Barcelona, and it was in the height of summer. There was a festival next to the train station on the beach, and lots of young people arrived on a late train, and instead of going through the underpass, they crossed at the back of the train and were hit by a high-speed train which killed 13 of them and injured many more. It was a dreadful accident. But if you look at the causes, there's a lot of indicators there that are saying high risk, young people near the track, in high spirits, high speed train, late train. It was known that there've been previous incidents of people trespassing across the railway here. So we've linked the data to this. So we've got social media, we've got CCTV, we've got GPS from the people from the revelers, station design, close calls. Were the close calls, safety management issues, timetable data, emergency services, they were already present. So if you look at all this data in its entirety, you're thinking this is not good. And this led to this very, very serious accident. Unfortunately, the Spanish report just blamed it on trespassing. And I would like to look at accidents like that much wider. So looking at the BD-ness of that particular accident, we rated the data sources against the variety of these data sources against the volume, velocity and veracity. And if it was high volume, we gave it an H. If it was low volume, we gave it an L. Same for velocity and veracity. And then we totted them up and we came out with a score of 67%. And we had a cut-off point. Anything over 67%, over 50% had high BD-ness, and below that it had low BD-ness, and it was probably business as usual. So the Hatfield one should have been business as usual. They should have known about it. It was an engineering problem. And also the same for the Compostela accident. This one was more complex and has more BD potential. So what have we come up with? Well, we've come up with the elbow tie product, and what we want to do with this is use a bow tie, which is a well-known accident causation model. There are various other ones like the Swiss cheese model, and the Nancy Levison at MIT's got the STAMP model for accident causation. There's various others. This is good because it's easy to explain and quite simple. You've got causes on the left, hazards in the middle, which lead to accidents on the right. On the left, you've got the opportunity to mitigate or to avoid the hazard by an intervention, and on the right, you've got the opportunity to stop the hazard becoming the accident. So you've got intervention points. So what we want to do is link these data sources to these intervention points. This is the basis of our model, and this is what we're working on. So we want to flag heightened risk. Now each one of these data sources has got value in itself, and what we're going to do is we're going to build this up. So we're already looking at derailment quotients and neural networks. We're looking at close calls using Bayesian networks. Each one of these has got its own value, but it's this complex interaction that we want to work on to flag up this high risk, and it's not a trivial job. But we want this all-seeing eye that will know when there's heightened risk, but also be visualized using a dashboard so that humans can make these interventions. So to conclude, the BD-ness of the analytics depends on the complexity, and it goes on a continuum from business as usual to highly complex, involving social media, weather, all these disparate sources. Intelligent algorithms are very important, and they'll change the way that both blue collar and white collar workers work, and this will include safety management. It may mean that analysts like myself are replaced. It's all about data and logic, and there are things that these algorithms can do very well. So the genie's out of the bottle on all this. There's no going back. It will change the way we work. The good thing is the models get better and better every year because they learn. And the problem we've always had in the railways is we don't learn. And we don't learn as well as we could, but these will enable us to get better every year because we will monitor when we don't get the controls right. Anyway, I'd like to show you our elbow tie product for everybody who has time after the event. Okay, I'll throw it on to questions now. Would you like to come and join me, please, Gary?